2.6, lesson 20, systems of linear inequalities. Terminology is systems of inequalities. Basically, it's two or more inequalities with the same variables. So we will be graphing two inequalities. Yesterday we graphed one. Example 1, here's your two inequalities. We have y is less than 4, x is greater than or equal to negative 1. I'm going to go ahead and graph y is less than 4. Note, less than sign requires a dotted line. Y less is 4 is plotted. Now, if I were to shade here, I could use my origin 0, 0. If I plug that in for this equation, 0 is less than 4. So right now, the shading that would be taking place would be below that dotted line. So that shading going below the dotted line. Next, you'd go ahead and graph your other inequality, which would be x is greater than or equal to negative 1. Greater than or equal to negative 1 would require a solid line. Now, you have 4 areas here. Here's area 1, area 2, 3, and 4. So there's 4 regions when two lines intersect. The shading cannot be in two different regions. Right now it's in this region and that region. So we need to determine what region does the shading belong in. It would need to work for both equations. So if I use this origin 0, 0, if I plug 0 in for y, 0 is less than 4, true statement. The shading works here. I put this in for the second equation. So I put in 0 for x. 0 is greater than negative 1, so it holds true. This is the area that should be shaded. This side would not be shaded, so we need to get rid of the shading. Also, to prove to you that just one side is shaded, is if I use this coordinate right here, this would be negative 2 for x, 0 for y. So negative 2, if I put in negative 2 for x, negative 2 is greater than or equal to negative 1. So that is not a true statement. Therefore, it could not be shaded over here. These are the only solutions that would work for these two inequalities. Example 2, both of these are in slope-intercept form, so we're able to use the slope-intercept form of graphing. I'm going to go ahead and graph this first one. Y is less than negative 6x plus 3. Intercept is 3. The slope is negative 6. Here's your other point. I went down 6 over 1, negative 6 over 1. Go ahead and construct that line. This line is going to be dotted, is less than. Next, I'll graph the following inequality. Y is less than negative x plus 2. Slope-intercept form of graphing. I'm going to plot my 2 for my intercept. My slope is negative 1, so down 1 over 1, there should be a negative line. Down 1 over 1. And here's my points. Looking at this inequality here, it is a less than sign, so it will be dotted line again. Again, I have 4 regions. Here's one region, second, third, and fourth. I need to figure out what region I need to shade. I can go ahead and use the test point where I pick a point in a region and plug that into the equation. Or you can use the boundary line. Here's your first equation that we graphed right here. We know that this is a less than sign, so the boundary down below would get shaded. And we know that this is a less than sign, so the boundary down below that line right here would get shaded, leaving us with this region here. Again, for the test point, a good point to use would probably be right here, your origin. You plug that into the equation. 0 is less than negative 6 times 0 is 0. So you'd end up with 3. You would have 0 is less than 3, which is a true statement. Therefore, this region would be shaded. For example 3 here, note that both of these equations are not in slope-intercept form, so you would need to put them in slope-intercept form. I'm going to go ahead And you can pause the video at any time, but I want you to go ahead and put it in slope-intercept form, each equation, and then graph of each of the inequalities, and then determine the shading. So go ahead and pause and do that and pick back up where we left off. First equation in slope-intercept form, we subtract x from both sides, giving us 3y is less than negative x plus 6. Divide both sides by 3, giving us y is less than negative 1/3 x plus 2. Here's what it looks like using slope-intercept form of graphing. And it also is a dotted line with a less than. Go ahead and do step 2, put the next one in slope-intercept form. I would subtract 2x from both sides, and we'd wind up with y is greater than or equal to negative 2x minus 3. Go ahead and graph. Again, this greater than or equal to would require a solid line. Your second inequality would look like this. Again, creating the 4 regions. We need to determine what region we need to shade. Again, you can use the point test. If we used 0, 0, I put 0, 0 back into your equation. 0 plus 3 times 0, so 0 plus 0 is less than 6. That is a true statement, so this is the area that would need to get shaded. Moving on to our last example here. I have a realistic example. Example 4, in order to be elected president for the United States, candidates must be at least 35 years old and win a minimum of 270 votes from the Electoral College. A says define the variables and write a systems of inequalities. I'm going to say, using this, that 35 is talking about an age, so that'll be x. And 270, since that was second, I'm going to say that that is my y, so my y value is talking about the votes. So x is age, y is votes. X, your age has to be, your age, x, has to be greater than or equal to 35 in order to be the president. Y, your votes, have to be greater than or equal to 270, according to our scenario above here. So now you have your 2 systems. Now you need to graph both systems. And B says graph the systems of inequalities. So we'll go ahead and graph that. Now in order to graph that, we need to, the rest of our table here, we need to have our axis is labeled. Our x-axis would be age, our y-axis would be votes, and we should probably come up with a title. Now that we've filled in our axes, titled our graph, we're going to go ahead and determine the intervals that it needs to go up by. I'm going to say age. I'm going to go up that each of these intervals will go up by 5. And on my y-axis for votes, I'm going to go up by intervals of 25. Next, I need to use my 2 inequalities above. First inequality I'm going to graph is x is greater than or equal to 35. Note, greater than or equal to requires a solid line, so x is greater than or equal to 35. There it is, graphed. Next, I'll graph our votes. Our votes have to be y is greater than or equal to 270. Again, that greater than or equal to require a solid line, so here's about 270. Now we need to determine for the election which, we have our 4 regions here again. Here's a region, there's a region, and the other 2 regions. We need to determine what holds true to make a presidential election. Well, it should be, looking at your graph, you know nothing's down here is going to work. Anything below 270, you're not going to be a president. Anything below the age of 35 is not going to be a president. So it'd only leave one section here to shade. The ones that are 35 and above, and you receive 270 or more electoral votes. So that's the area that needs to be shaded. And here is our shaded region. Name one possible solution. It can be any solution. Well, the solution can be, we know that our x value has to be 35 or above, so I could say a possible solution would be 40, talking about 40 years old, and they could have, they need to have at least 270 votes, so we could say that maybe they have 300 votes. That would be a possible solution. Looking at example D, they give us, is 52 and 235 a solution? Here we would state no, and we'd have to have a reasoning. So our reasoning here is no. Yes, it does make the age requirement of 52. That is obviously 35 or better. However, the votes of 235 have to be at least 270. So in order to be president, you must be at least 35, have a minimum of 270 votes. The votes in this solution only show 235 as to why it is no. This concludes lesson 20.